In this video, we'll be taking a look at neural networks. Neural networks are a form of machine learning better suited for certain kinds of problems. For example, there's this data set called the MNIST data set, and essentially what it is it's a bunch of 28 by 28 pixel images of numbers, and using a neural network, we can have our computer try to determine which image corresponds to which number. This has been a difficult problem for computers in the past. You can think of when you had to sign up for something. You know how there would be a little, you would have to write a series of random numbers or letters that were drawn. Well, that was so that computers wouldn't overwhelm their servers by creating fake accounts. But as machine learning is progressing, you've probably noticed how some of those have evolved, and now it's no longer determining what the letters consist of. It's actually full-blown images, and you have to, figure out if there's a train in the image or whatever else. And those problems are pretty easy for us humans to do, but for computers it's very difficult. Anyways, that's enough background information. I'll dive into what a neural network is now. So let's take the example of the MNIST dataset. What you're going to have is you're going to have a series of inputs, and you're going to have 28 by 28 inputs. So every single X value here is going to correspond to one of the pixels. And so these circles right here are neurons, and for every input it's going to go in every neuron. Now we can have any number of neurons here, so there theoretically could be a lot more than 4. Any neural network with more than one layer is called a deep neural network. And so we'll have another layer right here of neurons. And again, for every neuron in the previous layer, its output will enter a neuron in the next layer. And then finally, we'll have the classes at the end. Oops, how much should I go on there? And the classes are going to correspond to the numbers. So this will be 0, this will be 1, this will be 2, and then it would go all the way down to 9. And so the way it works is for every connection, there will be a unique weight associated to it, as well as a bias. And so assuming in the drawing, this pixel corresponded to a black portion, let's say that's a 1, well, the 1 will be multiplied by the weight. It will be added by the bias. So it will be summed with the bias. And then it'll enter this neuron right here. And if we were to zoom in as to what goes on in that neuron, well, essentially there's two parts to it. The first is it's going to sum all the inputs going into it. So for the neuron right here, you can see that, you know, every single input is going to be entering it, and so all those are going to get summed. And again, every single connection has its own unique weight and bias, so all these different values are going to get summed together, and it's going to pass through, oh, that was really bad, oh well, a activation function. It's pretty bad too. And essentially what the activation function does is it determines whether the neuron will fire or not fire. So in our brains, our neurons are either on or off, and in a similar fashion, you will, if it were a step function, essentially you would set a threshold, and whenever the sum is over that threshold, well then the output would be a 1. Otherwise, it would be a 0. Now, conventionally, you don't see step functions because it becomes difficult to determine which neuron successfully classified the image. And so what you'll see more often than not is a sigmoid function. And a sigmoid function kind of has a curve like this, where there's asymptotes, and the value ranges from, let's say, 0 to 1, but the output of our activation function doesn't necessarily have to be one or the other. It just has to be within that range. And then it becomes easier to determine which neuron successfully classified our images, and then that way we could train our models a lot faster. And so now we'll jump to the last part, which is the backwards propagation. So it passes through the activation function, it goes on to the next hidden layer, and then finally it reaches the end right here. Well, what we do at this point is we compare the output to our desired output. So let's say, did our neural network predict the right number for the corresponding image? So let's say we had an image of a 1. Well, did it determine that this was the correct answer? And if not, what we end up doing is we adjust the weights. And so in the beginning, the weights are just a random number, but as you go through multiple iterations, it will adjust the weights to try and increase the accuracy. And so the process by which the values go towards in this direction, it's called feed forward, and when you adjust the weights, it's called backwards propagation. Thanks for watching. If you have any questions, let me know in the comments.